How you deal with?
What is going on, everybody? It's your boy Average Leader here with another video, and today we're tackling number 1091, shortest path in binary matrix. This question is commonly asked by Amazon, Google, Facebook, Oracle, Snapchat, and this question was also requested to me by one of my most active subscribers, Santosh. I see you subscribed, I see you comment, I see you like my videos. So thank you so much for your interactions on the channel. It helps my channel out a ton by giving it more exposure to people that don't know me, and I very much appreciate you, my friend. And with that being said, if you guys want to see another problem done, just comment down below and I'll make sure to do that problem for you, and I'll even shout you out, okay? So with that all out of the way, here we go. And quickly, right before we start this problem, I want you guys to go and watch my minimum night moves video. You're going to see a lot of similarities in the problem structure as well as how we are going to create the solution for this problem. So go give that a quick watch. Watch it at 2x speed, whatever you got to do, just so you see how similar these two problems are. But all right, given an n by n binary matrix grid, return the length of the shortest clear path in the matrix. Okay, so immediately this line is telling me that a few potential solutions that we can use to solve this problem are either some type of dynamic programming maybe, or a breadth first search. Now, I'm not 100% sure just yet, but shortest path has been seen many times, and usually we can use one of those two strategies to solve a shortest path type problem. But I'm not sure yet. Let's keep reading and we'll see what we're going to use. If there is no clear path, return -1. Okay. A clear path in a binary matrix is a path from the top left cell, so 0, 0, to the bottom right cell, n-1, n-1. Okay, such that all the visited cells of the path are 0 and all the adjacent cells of the path are 8 directionally connected. Okay, so this here was the clear indicator for me. What this is saying is we have a starting position at the top left cell, 0, 0, and we have an ending position, which is the bottom right cell, n-1, n-1. Now, when we are given a problem where we have a starting position, an ending position, and we are told to find the shortest path of the problem, I am automatically thinking we need to use a breadth first search for this problem. Those are some big hints given to us so we can use BFS to solve this problem. So finally, the length of a clear path is the number of visited cells of this path. Okay, so let's look at this example number 2 on the iPad and see how maybe we can use a breadth first search. All right, so I wrote down example 2 straight off of Leetcode. And right now what we're trying to do is see if we can do a BFS on this grid to see if we can get the shortest path from the top left of the grid all the way to the bottom right of the grid. So in true BFS fashion, what we would usually have is a queue in our implementation, which would hold all the nodes or all the spaces of the grid that we would like to explore and look at all the neighbors of. And we'd also have like a counter or like something that's holding on to our length at all times of our BFS. So the first thing that we're going to do in our BFS is we're going to add our starting position to our queue. So what is our starting position? We're going to have this top left part of our grid in our queue, but how can we actually store this information into our queue? We need an object type which can represent each of these spaces of our grid. An easy thing for me that helps me visualize where we are in our grid is to treat each of these cells in our grid as coordinates. So I'm going to quickly label all of the coordinates of this grid. Our first number in each of these tuples is going to represent the row of each of our cells, and our second number is going to represent the column of each of our cells. So what we're going to initially store in our queue is the coordinate 0, 0. And also for our count variable, remember this count is going to hold the total length of our path that we're going to return at the end. And since in the problem it says that the length of a clear path is the number of visited cells of this path, and since we have already started at the coordinate 0, 0, we automatically have a length of 1 for our path. So I'm going to store 1 as our count for right now. And from here, we're going to pop off this node from our queue. And when we pop off an element from the queue, we're going to explore all of the neighbors of that element, or all of the adjacent cells from that cell. So in other words, we're going to look at the right, the top right, the top left, the bottom left, the bottom, and the bottom right. Now immediately we see that all of these directions right here, from the top right all the way to the bottom right, they are outside of the matrix's range. So we're not even going to look at that. And looking at the bottom direction, we see that that's going to a 1, so we're not going to look at that. And looking at the bottom right, that's also going to a 1, so we're not even going to address that. But the direction going in the right is going to a 0. So if we're given an adjacent cell with a 0, we're going to add that coordinate to our queue. So I'm going to add coordinate 0, 1 into our queue. And let's clean this up just a little bit. Okay, so after we're done going through all of the directions of our cell, we are basically done with that iteration of the breadth first search, and hence we've added all the nodes that we want to explore to our path. And after we're done exploring all of these cells that are neighbors of our current node, we've basically added another element to our path in our queue. And every time we're adding an element to our path, we're incrementing the length by 1. So once we're done adding all the potential neighbors to our queue, we're going to increment our count by 1. So now the count is going to be 2. Our length currently has 2 nodes, and that node is this one right here and this one right here. Okay, so now that we have that out of the way, we're going to go to the next iteration of our BFS. So next, we're going to pop off the coordinate 0, 1 from our queue. And since 0, 1 is right here, we're going to search for all of the neighbors, all of the adjacent neighbors from 0, 1. So instead of getting all messy one more time, I'm just going to go ahead and add the neighbors that we can add to our queue. So we see that we can add the right direction. We can add 0, 2 to our queue. So I'm going to add coordinate 0, 2. And we can also add negative 1, 2 to our queue. So negative 1, 2. And notice that we also have 0, 0 that we could potentially add to our queue. But now we don't want to do this. We don't want to add nodes that we've seen already into our queue, because it just doesn't make sense to go to this node again, because once we go to 0, 0, then we're going to add 0, 1 again, and then 0, 0, 0, 1. So this is like an infinite loop in our queue. And to combat that, what we can do is utilize another data structure. And I'm thinking we can use like a visited set. So a visited set, that's just going to be like another hash set. So let's create a hash set also. And I'm going to shift this down. I also see that our queue is about to be full, so I'm just going to make this like a bigger queue here. So we're going to have a visited set, and it's going to be a hash set. And in our hash set, every time we add an element to our queue, we're going to store it in our hash set as well. So far we've seen coordinate 0, 0, 0, 1, and we just added 0, 2, and negative 1, 2 to our queue. So I'm going to add 0, 2, negative 1, 2. And this way we just ask ourselves one last question before we add a cell to our queue. Have we seen that coordinate in our visited set already? Since we've seen 0, 0 in our visited set, there's no need to add it again to our queue. So that's what we're also going to keep in mind while we're going through our paths. So now after we're done going through all of the neighbors in this current iteration, what we're going to do is we're going to increment our count by 1, since we're basically increasing our length by 1 in our path. So now we're going to pop off 0, 2 from our queue, and at 0, 2 we see that we can only go down to negative 1, 2 and 0, 1. But we've seen these coordinates in our set. So we have 0, 1 here, negative 1, 2 here. So we're not going to add any of those to our queue anymore. And finally, in our queue, in this iteration of our queue, we also have negative 1, 2. So let's pop off negative 1, 2. And at negative 1, 2, we don't want to add the top. We don't want to add the top left, since we've seen those already. But we can add negative 2, 2. So let's add that into our queue. And we'll also add it to our visited set. And after we're done exploring through all the nodes in that iteration, we're going to increment our count by 1. So now the final step that we'll do is every time we pop an element from our queue, let's just do like a quick check to see if that x and y coordinate matches the n-1 coordinate in our grid. So in this case, our grid has a length of 2, 2, and you'll see when we code it out, we actually account for this. For now, we can just like pretend to take like the absolute value of this, and we notice that the x and the y coordinates are the same. So after we have reached our target coordinates, all we can do is return our count that we've been keeping track of so far. So we see that we get 4 here, and that is actually the solution to that problem. If we can't find a proper path in our grid, like let's say we're given this grid right here, we see that if we try to do a BFS on coordinate 0, 0, we'll get this node, that cell, and if we do a BFS on 0, 1, we get that cell. But after we're done here, we can't add any node after that because those cells don't have a value of 0. And basically, we just end up with like an empty queue. So after our queue is empty, if we still haven't found a path where our last node in our queue has the same x, y coordinates as the length of our matrix, like 2, 2 in this case, then we're going to have to return -1. So if we can't find a path, we're going to return -1. And the last thing that I think we need to keep in mind is we start off by adding the 0, 0 coordinates to our queue. But let's just say at the 0, 0 coordinate, we have a cell with a value of 1. And also at the final bottom right cell, we have a value of 1. If either of these two situations happen, we should also just return -1. There's no need to start any type of BFS if we don't have a proper starting or ending value. So with all these things considered, we see that a BFS is possible. Let's go ahead and dive into this code. All right, who is ready for some code? I know I am. So first things first, you guys know what I like to do. I like to start with asking the question, what are we trying to return? Well, we are trying to return the shortest path, and that's going to be an int. And I usually just like having it called like count or something, but in this case, I'll just call it length. Length equals, and remember, since we like automatically start by adding the very first elements, the very first cell 0, 0 into our queue, I'm going to start with a length of 1. And at the end, we can just return this length. Now, if you guys feel more comfortable, starting a length at 0 and then returning a length plus 1, go for it. That's all you. But I think for me, it's just easier seen as starting at a length of 1. And from here, let's also initialize the data structures that we're going to use. So we're going to use a queue. And what is our queue going to hold? We decided earlier that we want our queue to hold some coordinates, so I'm going to make a coordinate class in just a second. So it's going to be coordinates queue equals new linked list, and this will be our queue for the whole problem. And next, before we forget, let's make our coordinate class. So I'm going to make this a class coordinates, and in this coordinate class, oops, spelled that wrong. In this coordinate class, we're going to have 2 instance variables. We're going to have the x and y, which is going to represent like our row and column that we're going to have. And I think, maybe it might be better to see it as row col. And we're going to have like a constructor that is basically going to take in our row and col, and it's going to initialize our instance variable row and col to the row and col that we're going to pass in. So what I'm going to do is say this dot row equals row, and this dot col equals col. So we have a proper coordinate class here, and since this queue is going to hold coordinates, this should work properly. And we're also going to keep a visited set ready to go. So I'm going to make a hash set. And this hash set, there's one of two things we can do. We can either store coordinates in this hash set, but if we store coordinates, we need to define an equals method within our coordinate class. Or we can do something that's a little bit easier, and we can just have it hold strings. And every time we pop a coordinate off from our queue and add it to our hash set, we're just going to add like some quotes to that coordinate to make it a string. So this string hash set we'll call scene equals new hash set. And I believe we're done creating all of our data structures that we're going to use for this problem. So now all we have to do is add the very first cell to our queue. So how I'll do that is queue.add new coordinate 0, 0. And I'll also add the string 0, 0 to our hash set, c.add 0. And I'm going to have a comma that'll separate the row and column that we're at that particular moment. So, all right, so now that we have all these things ready to go, we can just start writing out the code for a normal BFS. We're just going to go through a normal BFS implementation. So while the queue isn't empty, we're going to grab the size of our queue at that particular moment. And all we're going to do is iterate through all the cells that are in this size. So for int j equals 0, j is less than size, j plus plus. The first thing we're going to do is pop off the first thing that's in our queue. So we have a coordinates p equals q dot poll. And from here, I want to grab the particular row and column that we're at that particular cell. So what I'll do is I'm just going to make a new variable int px equals p dot row and int py equals p dot call. And after we have these two things, all we have to do is iterate through all of the potential directions that we can go to. Now, how are we going to simulate going to the right, the top right, the top left, and so on and so forth? How are we going to simulate actually going through directions? Well, we can hold the directions using some extra storage at the top of our method here, and I would just call it int xdir, and this will hold like all our directions in the x direction, and int ydir is going to hold all the directions in the y direction. Oh, and I also forgot that since these are arrays, I need to add these little square brackets here. And I think the biggest thing to remember is every time we create storage that's going to hold directions at each index at both of these int arrays, that index is going to represent the xy pair for the direction that we want to go to. So for example, let's say I want to go in the bottom left direction. So I'm going to have -1, -1. So this pair at the 0th index is going to go in the bottom left direction. And then let's say I want to go down in the bottom direction. So I'm going to have 0 and a -1 here. And then let's say I want to go to the bottom right. I'm going to go 1 and a -1. So each of these indexes is going to represent the pair of our xy direction that we're going to go into. So let's just populate the rest of the directions. So we have these are all the directions that we're going to go through. And now all we have to do is iterate through our directions. So I'll say for int I equals 0, I is less than xdir.length. And since they're both xdir and ydir are the same length, it doesn't really matter which one we iterate through. And we are going to add each of these direction pairs to our current coordinate. So I'll do int new x equals px plus xdir at the index of I. And I'm going to do the same thing for the y direction. So ydir py new y. So now this is going to represent the neighbor, a potential neighbor that we can go to. Now remember, we can't go through all the neighbors. The neighbor has to be within the bounds of our matrix. The neighbor also has to be a 0, and the neighbor can't be in our visited set that we've seen already. So to make sure that we're following all those things, we're going to have a really big conditional that's going to take care of all those things. So if new x is less than the grid.length, so here we're checking to see if we're in the bound, if we're not going over in this direction of our matrix length, and new x is greater than or equal to 0. That way we're not going under our matrix length. And we do the same thing for the y's, and new y is less than grid.length, and new y is greater than or equal to 0. All right, so these are all our bounds checks. Okay, we're making sure that our coordinates and stuff are within our matrix. And our grid at the index of our new x and new y equals 0. So this is us checking to make sure that we're not going to iterate through any ones. And finally, and our hash set hasn't seen that coordinate pair. Well, first, before we do that, before we check that, let's make a new string s equals new x plus comma plus new y. So, and our seen hasn't seen or hasn't contains our s. So only after all of these conditions are checked, only then are we going to add that new coordinate to our queue and also to our hash set. So q.add new coordinates, if I can spell, coordinate new x, new y. And also, we're going to add this to our visited set, but we're not going to add the coordinate. We're going to add the string that we created out here. So s. So after we do all this basically will do our BFS for us. Here we're iterating through each of the cells that are within our queue, and here we're just going through all the directions that we want to explore, and we're adding all the possible ones to our actual queue. So remember, the whole point of this is to return the shortest path in our binary matrix. So when are we going to increment our path? When we're done iterating through all of our nodes and appending all the potential nodes to our queue, that's when we want to increment our length. So after all this, we're going to do length plus plus. And this is like very similar. This style is very similar to like a level order iteration in a BFS. This is like a very standard kind of thing where at the very end of our inner for loops, we'll have like a incrementer at the very end, which will represent like the level that we're currently at. But this is kind of the same thing here. And now when are we going to want to return our length? Well, we said earlier that if once we pop off a point from our queue, if that px and py is the same coordinate or like is the same position of our bottom right of our matrix, then we're going to want to return the length. So all we have to do is check here if px equals grid.length minus 1 and py equals grid.length minus 1, then we're going to return the length. And that is all we're going to have to do for this problem. So let's just check to see if I made any mistakes. I'm going to run this code. All right, no mistakes here. Now, the last thing that we're going to want to check, we're checking for every case that we could potentially fail, right? So far, this is only going to work if our top left is 0 and our bottom right is 0. But remember, what if we have a 1 at the top left? And what if we have a 1 at the bottom right? Then we're never going to get a good path, right? So before we do any of this, let's do a quick check to see if our top left and our bottom right are zeros. And if they're not, we're just going to return -1. So if grid 0, 0 equals 1, or grid grid.length minus 1, grid.length minus 1 equals 1, then if that's the case, we're just going to return -1. Nice and easy. So I'm going to rerun, make sure that I did not spell anything wrong. Okay, and let's submit this.
They ask you how you are, you just have to say that you're fine when you're not really.
Okay, so let's see. I made an error somewhere. Ooh, you hate to see this, guys. You hate to see it. Oh, okay. All right, guys, listen. I am extremely sorry for this. I don't even know why I did this. But remember, if there's not a proper path that we can get from the top left all the way to the bottom right, at the very end, we are going to return -1. I don't know why I decided to return length here, because only if our px and our py equal that bottom right corner, if the coordinates of that bottom right, only then we're going to return length. If this never triggers, we're going to return -1. So let's run this on that example that we missed. All right, that works. My bad, guys. Let's submit this. All right, a whopping 109 milliseconds. We're faster than 5% of the Java Online submissions. Woo! That's looking real nice, right? Oh no, we don't like that. Oh dang it. Okay, I thought I can get away with this, but no. At least we're faster than 5. You know, we could have been faster than only like 3%. But hey, okay. So this is a good start. Okay, now I always preach like the reason I think we should do a ton of problems is so we get exposure to as many types of problems as we can. And I decided to base this video and the answer to this question based off of my minimum night moves video and that question. And that one really helped prime me for this video. So if you notice, most of this code is actually very similar to that video over there. But now I'm trying to think, how can I make this faster? How can I be better? I don't want to be faster than only 5%. I want to be faster than more than 5. At least give me like at least 10. So how can we make this a little faster? Now the first thing that I'll think of is there any particular data structure that we don't necessarily need? If we can represent a data structure using another primitive type or like a primitive storage type, then we can improve our time complexity like much faster and make it that much more efficient. And the reason I used a hash set was because I was thinking in that minimum nights moves video, we needed a hash set to contain all of the coordinates that we've seen already. But in that problem, we had a board that was infinite. We didn't know the size of that board. But in this case, we know the size of the board. We have like a grid of a certain length. And if we have a grid with a certain length, is there any way that we can represent that board and specifically represent all the nodes that we've seen so far, all the cells that we've seen so far? Well, we can actually create another fake, like a dummy board that will represent all the nodes that we've seen so far. So all I have to do is make another board. And in this case, I can either do like an int board or a Boolean board. But I think it's easy for us to see that if we have like a Boolean double array, every time we add a node to our queue, we'll just make that coordinate in our board a true value instead of false. And that way we'll just check to see if our Boolean board, which I'll just call like visited, if our visited Boolean board equals true, that means we've seen that node already. We've seen that cell already. So we don't want to visit that node one more time. So by replacing the hash set to an int array, a double int array, we are saving so much more time. So all I'm going to do is if visited equals new Boolean, and the dimension of this visited grid, of this visited double array is going to be the same as our grid dimension. So new Boolean grid.length, grid.length. So since this is going to replace our hash set, I'm just going to comment out this hash set, and I'm going to change every line. Every time we're adding something to our hash set, I'm going to change that line to the visited double array equivalent. So here we're adding 0, 0. That's equivalent to saying at visited row 0, column 0, we're going to set that equal to true. And here we're adding s. So this is just the equivalent of us making that new x, new y in our visited double array. We're just going to make that true at that coordinate. So visited new x, new y equals true. And also, we don't need the scenes dot contains s. All we'd have to do is if the visited at new x, new y isn't true, then we're going to want to actually go into this conditional and add the coordinate and also have our visited cell at that spot equal to true. So if I run this, let's see if I didn't make any mistakes. I'm going to submit this. And boom, immediately our runtime goes from 109 milliseconds to 72 milliseconds, and now we're faster than 7.83% of Java submissions. So it's still not where we want to be, but it's an improvement. If an interviewer asks you, hey, is this the most efficient thing you can do? Is there anything you can change? This is a quick change that you can make. Now, finally, what did we do to increase our efficiency here? We changed an object type, a container holding object types, into something that holds primitive types. We changed a hash set holding the string object to a visited set, a visited Boolean array, which only holds Boolean, and that increases our efficiency. Where else are we making an object? Well, it looks like this coordinate is an object, and this would be the last thing that we'd have to change here. Now, once again, for me, it was easy to see this problem as like a coordinate type problem. But is there a way where we can use like quote unquote coordinates without actually making an object class? well, maybe we could represent a coordinate using an int array. And in our int array, we'd have the x and the y coordinates within our int array. So the 0th index would always be the x coordinate, and the first index would always be the y coordinate. So if we were to change all our coordinates here to int arrays, all right, I just have to change all of them to its like primitive type equivalent. So now here we're adding new coordinate 0, 0. That would just be equals new int 0, comma 0. We would do the same right here. We're not popping off a coordinate. We're actually popping off an int array, and then our px. We're not accessing the row instance variable of each of our coordinates that we're polling. We're actually going to access the 0th index for our x's and our first index for our y's. I believe that is all the changes that we have to make for this to work. So let's run this code.
Fine when you're not really fine, but you just can't.
Oh, I guess I missed something. Oh, we're not actually doing new coordinate, new x, new y anymore. We're going to do new int, and in that array, we're going to hold a new x, new y coordinate, and let's run this. And look at that, that works. So let's submit this. What the fuck? And finally, the last thing. Sorry guys, I know this is a little bit of a longer video, but the last thing we need to do is we keep making a new string every single time, but now we don't need this new string anymore. So I'm gonna comment that out. And this should be the last step that we need to do in order to increase our efficiency. And look at that. We went from a whopping 74 milliseconds all the way to 13 milliseconds. And drastically improving the time complexity here. The reason I did this problem was to show us that even though we did an approach to a similar problem in the past, it doesn't necessarily mean that that approach is going to be the same exact thing we need to do for all types of problems. And the reason we did this coordinate class and we had a hash set in that previous minimum night moves problem is because we were told that the board was infinite. It was an infinite board. But now there was actually one key detail in that problem that I actually missed. And it told us that the constraints of our XY coordinate that we're actually passing in, those cannot exceed 300. So what does that mean? That means at the worst case scenario, we're going to pass in and look for the X coordinate at 300 and the Y coordinate at 300. So that means our board has a max length and width of 0 plus 300, 0 minus 300 in the x direction, and then also the same in the y direction. So if we actually redid that problem the same way we did here, and we changed our hash set there to a Boolean visited double array, and we changed what we store in our queue as a bunch of int arrays, we see that even that time complexity changes drastically for us, and it actually becomes much more efficient. And this is something that I'm going to keep in mind for all future grid problems that I'll even do. I'm changing my approach so that we get the most efficient solution every single time. So with that being said, let's just finish off this problem by discussing the time and space complexity. The time complexity, well, let's see, what are we doing here? Well, I guess the bulk of our complexity happens within this while loop. So we're iterating through all of the nodes within our queue here, and we're only looking at each of the node at most one time, since we have this visited double array that's in charge of telling us what nodes we've seen in the past. So at the worst case scenario, since we can go through all of the elements in our grid, our time complexity would be O of n. And in our space complexity, well, we have our queue, which at the worst case could hold n nodes in our graph, and that means, or in our grid, and that means our space complexity is also O of n. So that is how you do this problem, guys. Hopefully that made some sense. I know this was a longer problem, but I hope my points got across that even though we know how to do a type of problem in the past, we can utilize the same type of strategy in this problem, but we're always trying to improve ourselves. We're always trying to become more efficient. And for me, it was seeing this initial 109 milliseconds that kind of told me that, hey, maybe my solution wasn't the most efficient. But now this one looks like a much more efficient solution than that first one. So anyways, if you guys like this video, go ahead and give this video a big like and subscribe to the channel. Also, please feel free to comment down below. Let me know what problems you'd like to see done, and I will make sure to do them for you guys. And yeah, hope you guys have a great rest of the day, great start of the week. and I will see you guys next time.
Girl, I got a question for ya. Can I get an answer?